Hi everyone, I'm Robert, and if you're curious, I'm from Slovakia, because I noticed that everyone, like most of the people, have like the country of origin written on the presentation paper, and mine is missing. It's because I'm too lazy and I didn't fill my profile, so sorry. And I'm from Slovakia. And I work as a software engineer in Kiwi.com. Kiwi.com is a Czech company, and I live in Czech Republic. And if you want to know what Kiwi.com is doing, just go to Kiwi.com and find out by yourselves. So I'm going to talk about bits and bytes of Python memory management. And as the talk suggests, it is going to be actually like bits and bytes. It's not like the complex structure or anything. It's mostly like things I found interesting and wanted to share with other people. Why should you care about Python memory management? Like, the truth is that in most cases, you don't have to. Like, 95% of your work, you don't really have to care about like how is memory being managed in Python. But if you hit those 5% or less of projects which needs like deep diving into like memory management in order to like if you want to avoid adding more computer power to your problem, and you want to instead optimize, and you want to save money, right? So all of the information here are probably related only to those 5%, and you don't need those information at all. So why should I care? Honestly, I think I've hit such problem only once in my professional career, which is not that long. By why I care? Well, I like to learn stuff, and what I think is that every year when you look back like where you have been year before, and you don't have a feeling like, yeah, I was really stupid, how could I write that code, how could I think of that? I think that in that case, your time is wasted. Like, you didn't spend as much time as you could into becoming better software developer, right? And yeah, that was one of the reasons I always try to learn new things. And one of those things happened to be Python memory management, because first time when I was at the EuroPython conference in Spain, and I met my current boss, which is our CTO in the company, he told me like, hey, did you know that, Python memory is never released back to the OS? And I was like, well, I didn't know, but okay, I guess. And the truth is, from most of it, it's the correct statement, but also it's not that correct. So I would like to explain you why and how Python returns like the memory, which is using back to OS. And also, the other reason, this is like the GitLab issue in our repository. There was this guy who was trying to search for memory leaks in code, and he was not doing it right, and he had like a really bad idea about how memory management works in Python. And also, it's really hard to test those things. And most of the time, these things are out of your control, because most memory leaks happens in some C-level language. So it's most of the time those are some C bindings you're using in your code. And also, maybe somebody will ask you such question in job interview, and that might be beneficial, I guess. So this is the most important statement about Python. Like, everything is an object. I was hearing this like many times before, and I never paid an attention to it. Like, most time I spent with Python, I realized that, yeah, everything is actually an object. You can use anything, and you can access anything, and you can change anything. And that's why metaprogramming is very easy in Python. So it doesn't matter if it's a function, if it's a class, if it's whatever else, everything is just an object in Python. And Python internally is using like referencing. All variables you have in your code are just stupid references to code objects in memory. And the other thing which is important on this slide is PyObject structure. You probably see it, but I will use this cool thing. So there are two important, I don't know how to say it, variables. I think it's not variable in structure. It's called something else. But first is object reference count. And okay, I should tell firstly that every object in Python is consisting from this structure. And the object reference count is keeping the reference count of the object used. I will get to that later. And the other, this is a pointer, and this is a pointer to the memory, like where the object is located. And if you are curious what is PyObject head extra, you don't have to be. This is something for debugging, and I don't even know what it is. I never use it. I never cared. This is Python memory management overview. This, as it is taken from file obmalloc.c, which you can find in C Python repository, like at the top, like this. This is a link where it resides. So I think I will share my slide somewhere, and you can go through it. Okay, what's important here? You can basically ignore like these three things because those are like out of your reach. And also kind of this one. This is management of Python virtual memory. This is where like all allocation to heap is happening. Like every time Python process needs more memory from system, this is where like where it happens, like where the memory is being allocated. What's more interesting is Python object allocator. This is a thing that takes memory from this layer, like from the heap, and allocates their objects. And in this structure resides like all of the objects from Python. So how is memory being allocated? There are basically two options, like how the object is being allocated, and that depends on the size of the object. Whether like object can be bigger than 512 bytes or smaller than 512 bytes, and this relates to 64-bit system. I think it's half of that size in 32, but I guess nobody is using 32 bits and we shouldn't care about it, I guess. Allocation of objects which are bigger than 520 bytes are pretty like straightforward. It is using like the PyMalloc allocator to allocate the C memory. So if you ever code it in C, I think you have like the basic overview how that happens, and it's, I don't know, it's kind of boring. What I think is far more interesting and far more important for Python is are the objects which are smaller than 512 bytes. Because like most of the objects, as I told you at the beginning, everything in Python is an object, and as such, like there is a big overhead when using Python when objects are being created. Like you have so many objects there, and there needs to be like created in the most efficient way as possible, right? So Python came up with this structure. It's called simple segregated storage based on array of free lists. Basically, I think if you Google for free lists and Python, you should find some things related to that. The whole idea is oriented in like in between two levels of abstractions. Like the smallest abstraction is block, then there is a pool, and then there is arena. Like as I told you, like this technique is quite efficient for memory intensive programs, like when you create lot of objects on a run. Let's start with the block. Like each block stores precisely one object, and block can have a size in between like 8 bytes, which is minimum. Like no matter how small Python object you create, it will always take up at least 8 bytes. And like the upper limit is the already mentioned 512 bytes. Okay, and each block is like in a size of multiplication of 8. You start with 8 8 bytes block size, continue with 16, and 24, and so on, and so on, and so on, until you reach the 512, and that gives us like 64 categories of different possible blocks. And those categories are called in C Python code base classes. This was the first, like the basic structure. Then there is a pool. What pool does is it contains blocks. Pool has a size of a memory page usually, and that's also again usually 4 kilobytes. And in a pool you can store only blocks of the same size. And each pool can be either full, empty, or used. Like full and empty is, I think it's pretty obvious what that means. Like you can, it's either full and you can't put any more blocks into it, or it's empty and you can put as many blocks as you wish. And or is it used, and that's neither full nor empty. Yeah. Then next thing, used pools. Used pools are a way for Python to like efficiently manage the list of all pools, because the used pools are grouped by its class. So you have a list of 64 classes, and those are like objects to linked lists where like all of the pools with which are storing blocks of the same size resides. Yeah. So why I'm talking about use pools? Because there's nice follow-up to Deadpool. And that's the only thing why I put there, the use pools. I like Deadpool. And I hope you saw the trailer for a new Deadpool. Yeah, cool. So next one are arenas. And those are like most important from the memory management view, because arena is chunk of memory, and each arena takes 256 kilobytes of memory. Arenas are being allocated on a heap, and each arena can hold at most like 64 pools, and those pools are in mixed size. And what's important here, like when are people complaining that when they run their programs and the programs are taking more and more memory, and they are complaining that the memory is not being released back to the OS. The thing is that the memory is being released back to the OS only when like the arena is completely empty, and that doesn't happen very often. So that's why you can see like the memory growing when you like continue use your service or whatever. But it is important also to note that unused memory in arena is being used again. Like when you have some pool in arena and the pool is being full, and then because of the garbage collection and whatnot, the memory is being free, the pool can be used again. So you're actually not losing any memory because the memory can be used again. These two things, like the Python malloc stats or sysdebug malloc stats, this one I think it's only in Python 3. This will show you like how much arenas and pools and other things you are using. Like, did you notice like how I run it? I use it as an environment variable. I pass just one to enable it, and here you can see like, yes, here you can see like per different class how many pools are being allocated at the start of the Python, and how many blocks are in use and how many blocks are available. So when I start my Python 3 on macOS, on my current system, this is like how much arenas it is taking. And yeah, also there are bytes written here. So you can either use the environment variable to see like how arenas are being changed, or and this will like print. Yeah, now it's not going to print because it will print this info only when new arena is created. Okay, that's the basic stuff. Okay, this is a classic trick found on, like, it's regularly being posted to Hacker News. If you read Hacker News, you had to see it, or follow Twitter, or you live somewhere where is internet, you must have seen it. So there is this trick when you allocate integer which is small enough, and you compare those two integer using is, which is testing the equality, whether those two things are same object, like pointing to the same address in a memory. Then you can see that for 25.6 it returns true, but for 25.7 it returns false. So what's that? That's because like Python at the beginning, like as you saw, like all the arenas being allocated at the start, Python also allocates at the start like all integers in between like -5 to 257 excluded, and those integers are created and are always the same. Like when you use 2 or 5 or any number from that set, it's always the same object. If you want to ask why, well, that's because Python core maintainers decided like the best way to use it. Like this is the most used integers, and you want to save the performance overhead over like creating new integers. So you rather create them at the start and always use the same object. If you are interested more, like how those integers are working, you can visit CPython again, and the code is in a long Object-C file. And by the way, CPython is already on GitHub, if you didn't know that, because it used to be at some obscure site, which I didn't even really like. Yeah, strings interning. That's something interesting. I didn't know about this before I started creating this presentation. And this is something similar to small integers. Some integers are not being created again, like are being used again like the already created object, and some are not. And yeah, I would like to explain like what are the rules, how that works. So the first rule is that the interning happens at the compile time, and that's very important. That's why when you look here, like these objects are created at the compile time, but the join functions are being run at the runtime. So, and that's why like these two objects are same, but these two objects are different, because this was created at the runtime. That's the first like important rule. And the next important rule, like only strings which are composed of ASCII chars, and the ASCII chars are either chars like the letters, or digits or underscores are being interned. So if you look here, I use the exclamation point, and you can see that the objects are not equal anymore. Also, yeah, bytecode optimization plays its role too. Like, what does it mean? When you use string concatenating, like foo plus bar is foo bar. This will again be true because like the foo plus bar is being concat thanks to the bytecode optimization at the compile time. Yeah. And there is really awesome article about it. You can find it here. It's very easy URL, and I advise you to read it. Yeah, and also, I almost forgot. If you want to force like the interning of strings, you can use the SYS.intern. And every time when you pass the string to SYS.intern, it will firstly look up in its own dictionary to try to find whether the string already exists, and if it does not, it will create a new object. And also, all this interning is used by default at the classes. Like every time, like the class by itself is also a dictionary, and when you access some methods or whatnot, you are using actually a dictionary, and dictionary lookups are using the SYS interning. So that's also interesting. Yeah. As I was mentioning at the beginning, the issue with memory leaks, with my colleague tried to solve. One of the mistakes he did was that he was trying to use SYS.GETSIZEOF to find out the size of the object in Python. Actually, SYS.GETSIZEOF will not return the actual size of the object in Python. It will return the size of the structure. And you can see it, for example, yeah, you can see it on this example. Like when you take the integer list and string list, and obviously like a string has a different size than the integer. But when you call the getSizeOf on a list of string of the same size as the integer list, you receive the same number. And that's because like the structure of a list, it doesn't contain those values. It only contains pointers to those objects. So when you would look at the list, you would see only like list of pointers to different objects, and every pointer has the same size. I think it's 16 bytes. So only the memory consumption directly attributed to the object is accounted for, not the memory consumption of object it refers to. When you know like how the memory is being created, you should know also how memory, like the garbage memory which is not being used anymore, is being collected. And Python by itself is using two methods. First method is reference counting, and the second is generation cyclic GC, as garbage collector. Do you know this guy? Do you know why is it here? You should watch Sopranos. And he's Italian, Mafian or whatnot, and he works in garbage business. So reference counting. This is very like naive idea how, like if you remember like at the beginning how I showed you blah 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 blah. Yeah. This object reference count. This is actually being used in the reference counting. Like every time when you reference your object somewhere else, or you assign this object somewhere, the object reference count increases by 1. This is very simple, and it's also very efficient. But what the problem is that it can't detect reference cycles. And do I have an example with reference cycles? No, I think later. Yeah, you can get the reference count of the object. Like when you look here, like the number 2, as you remember, as I told you about the small integers and them being used again, like not created again. So every time you use 2, you are using the same object, and every time when you use the same object, the object reference count gets increased. So that's why this is like that's why the get reference count returns here 131. This is actually like the vanilla in Python interpreter. There wasn't any code before. This is what it returned when I tried to get the reference count from the integer 2. And also, yeah, I actually wanted to ask you, do you know why there it is being like 2, like the reference count being 2? What? Yeah, you probably, I didn't understand very well. The thing is that when you create the foobar, like the string, then there is like reference count 1, and once you pass it to the function, it gets increased by 1 again. So that's why there's 2. That's what you meant? Yeah, cool, thanks. So what's next thing very important about reference counting is that it can't be disabled. Like no matter what you try, it will be always there. And yeah, like when count reaches 0, like the deallocation function is being called and the object is being dereferenced. Okay, so about generation cyclic GC. So what this does is that it's solving the problem that the reference counting can't solve, and it's trying to find cycles. It runs periodically, like when you reach certain threshold, the garbage collector is being run. The objects, when you create objects, they are stored in the generations. Like every new object is being stored in the first generation, and the lower the generation, the more often the garbage collector is being run for that generation. And also, you probably know this, but when you run the garbage collector, like all of the execution code is being frozen, and it waits until the garbage collector finish. Yes, this is the example with cycle. You have a list, and you append the same list to that list. You get the address of that list, and you print the reference count. And you can see that the reference count is 2, because this is 1 and this is second. But when you delete the list, you would expect that there is no list anymore, right? But when you run like the reference count, when you try to print the reference count of the object, you get 1. And that's why there is a cycle, and even though you dereference like the object, it is still being referenced somewhere. And that's where, like when you run the GC collect, it will find these cycles and it will deallocate those objects. And yeah, I should tell you that this is using the C types. And you can use C types to inspect the C structures of Python objects. As I told you, like when GC runs, your code gets frozen and you have to wait until the GC finishes. What you want to do, maybe to like increase the CPU performance, is to remove cycles from your code. And you can use object graph module for that. What it does, it simply takes your object here, and you can pass it to object graph show reference function, and it will print you graph of your object. Like right here, there are no cycles, right? And once you find those cycles, you can use the vgref to get rid of them. Like if there is no other option, like you get rid of the cycles by passing the objects in a different way, but there is also an option to use weak reference. And what weak reference does is this. Like this is a cyclic reference. And you can see that you assign the A object to B, but when you delete A, the B is still pointing to foo object. So it's not dereferenced, and it's not therefore garbage collected. So what you can do instead is you can use the weak reference for your object A. And here you can see how it works. Like when you call the B, like the weak reference, it returns the object. But when you delete the object, like the original object, and you try to call the weak reference again, it will return none. This might be useful probably when you are loading some files. And you don't need the content of the file later, and you need it to only something like right now to next thing you can do is to disable GC. As I remember, I told you you cannot disable the reference counting. Even though you disable the GC, you only get rid of like the garbage collector, which is trying to find the cycles and remove them. So all others, dereferencing will still work. And maybe you read these cool articles. It's actually from Instagram. The first one was their attempt to disable the garbage collector, which they did. They gained like 10% CPU performance increase, and also they saved, ironically, a memory from doing so. But later they found out that without the garbage collector, in the long run, the benefits outruns the pros, because the more your program is running, there is the bigger chance that the cyclic references are being introduced, and more memory is being allocated. So what they did instead is they introduced to Python 3.7 a cool feature called GC freeze, and the problem they were having was originating in forking processes. So if you are using the VCG or GUnicorn, and it works in a way that it starts the master process and then it forks like all the workers from the master process. And the problem is with copy on write, which is how is Python memory, Python memory in OS being shared across forked processes. The thing is that when you use objects in Python and you are only using them as a reference and you are not editing them, you are actually performing copy on write, because every time you use object, you are editing the object because you are increasing the reference count of that object. So that's count as a copy on write, and every time you do that, the memory from the master process is being copied to your fork process, and that creates a big overhead on the GC runs. So what they did was that they introduced GC freeze, and what you can do in Python 3.7 is that before the fork occurs, you can call GC freeze, and what it does that, as I told you, there are like 3 generations in garbage collector. This actually creates 4th generation, and that's the permanent generation, and that generation is never touched. So when you call GC freeze, all your objects are being moved to that permanent generation, and GC never touches that generation, and that has benefits of increased performance, and I think also it saves memory, because the objects shouldn't be copied anymore. And actually I found out about that today when I was preparing this presentation, and I think this is the best thing you can get from this presentation, because it's actually something usable. And so if you are using Python 3 and you will like update to Python 3.7, look into the GC freeze and use it in before forking processes. Yeah, this will be very fast. There are some processes you can use to track memory usage. First is Pimpler. What Pimpler does? It actually prints like all of the objects. Like the idea is that you use the print diff in between different function calls to see like which objects weren't dereferenced. This is very helpful for finding memory leaks, because what would you do is you run this print diff, then you run some function which you think it's leaking some memory, and then you run the third print diff again, and you will see like the difference between those two calls, and you can find there some objects which are not being dereferenced. And the next thing is pytracemalloc. What pytracemalloc does is it prints like the memory usage per file. This is one of the things it does that I found most interesting. Yeah, you can see you start the tracemalloc, you run your code, then you take the snapshot after your code is being run, and then you can print like all of these stats from the snapshot, and it's being ordered by the most usage as a first. That's kind of interesting. Probably we are not going to use it, but it's good to know about it. Yeah, and that's everything.